Bohannon, who will tell something more about lenses, namely incremental relational lenses. Go ahead.
Right, thank you very much for the introduction. First of all, I'd like to say that this is joint work between me, Rolly Pereira, and James Cheney, both of whom are in the audience today as well. So I'd like to begin with why relational lenses? Why is this interesting? And you know, in our modern web application world, we'll often have the situation where we have, you know, some server and some clients that are connected via the internet, which in this case is represented by this small little black box, which some of you might know. And, you know, typical scenarios that the client will want a subset of a very large database, and then that client will want to make changes to the subset, and then it wants to send it back to the server and have the database updated. And it's this last step that, you know, there isn't really an easy way to do automatically. And this is where, you know, lenses are great. So I'd like to start with some background information. From the previous talk, there's a small example of lenses and what the classic lens function signatures looked like. So we have generally we have a get function and a put function, and the get function takes our underlying data structure and returns the same or subset of the data, which we call y. And then we have a put function, which allows us to take the original x and an updated y, and to give us an updated x. And we call a lens well-behaved when it satisfies two properties. The one basically saying that if we put something and try to get it back, we'll get the same thing, as well as if we get something and put the same thing back without making changes, then it shouldn't make any changes itself. And then we have relational databases, which many more will be even less familiar with. Relational databases are basically just a collection of tables, and what we can do is we can define a query over these tables so that we don't have to download the entire database and perform some computations. Instead, we can just say, hey, database server, I only want these records, or I want the data in this or that format. So we can filter, project, and join, and this is sort of the link syntax for that. And then we have the relational view update problem, which is actually something that goes back to sort of the 20th century, 70s, 80s, when database servers were new. They realized, hey, wouldn't it be cool if we could, you know, perform updates on a view which is defined as a query. But they noticed that there's a few issues with that. So, well, first of all, their main goal was, well, how can we translate and insert an update or a delete statement to the underlying database? And they weren't necessarily interested in what does it mean to be well-behaved. And they did realize that the put direction isn't necessarily unique. So if you have a join, then it's not exactly clear if you should delete from the left or the right table in all cases. And the result is that there's very little database server support. So if a database server does support view updates, then it'll always say, okay, this has to be exactly in this format, or in most cases, they just don't support it at all. And then in 2006, relational lenses were introduced by Aaron Bohannon, Benjamin Pierce, and Jerry Vaughan. And what they gave us was a relational algebra expression, which I don't want you to try and understand, so that's shown on the right-hand side on the slide, which just says you can calculate the well-behaved update using this expression. And they defined different lenses for selections, projections, and joins. And they gave us a type system which allows us to tell when sort of lenses could cause issues with well-behavedness. And we're trying to extend on this work and make it practical for typical web client situations. So I'd like to start out with a small example. We're using DBLP. So DBLP is a computer bibliography library. And, sorry, computer science bibliography. And we've got two tables. The one table contains the conference papers, and another contains the corresponding authors of each paper. And let's say we get a request saying, you know, there's something wrong with one of the entries for Richard Peruta, so we're told let's go investigate. And we define two lenses to first of all join the two tables to get all the information and to then filter by an author. And if we then look at this, we can see in the third entry here, that contains alpha trellis. It's, you know, if we try to render that, most, you know, renderers will say, well, we don't know what the command alpha trellis is, so this is something we'd like to fix. And one way we could fix this is to replace the \alpha with an actual Unicode alpha. And then what we'd like to do is we'd like to put this data back. So what we want to be able to do with relational lenses is just say, okay, data prime is the changed version of this, and then we just want to call lens put and have everything handled by the software. And with existing relational lenses, what would happen is because we've just got a relational algebra expression, we'd have to recompute the entire tables and databases, which, especially with DBLP and 2 million entries, is particularly slow. So what we do instead is we calculate a change set, which is in this case considers all the added and removed records. And then we translate this change set to the view, or from the view to the underlying tables. And then the changes to the underlying tables can just be converted into SQL commands and executed. Okay, so to excuse the pun, most of the incrementalization stuff was sort of the spotlight was stolen by Colonel Elliott yesterday on his presentation on automatic derivation, but nonetheless, I will go through my, or how we did it. So, as I said, we get this relational algebra expression from the existing work, and in this case, again, don't look at the details of the equation, all we know it's an equation, and we want to calculate a delta for this put function so that we can, instead of giving it an entire updated n, we can just give it a delta n to calculate a change for the underlying tables. And so the question we're trying to answer is, if we know f of x, what is f of x prime? And this is basically the concept of incrementalization by differentiation. So the first question was, well, okay, what is actually the difference between x and x prime? And in our case, we can describe changes as, given a table, we can add and remove rows, and so we'll describe changes as sets of added and deleted rows as well. And this we'll call delta m, which contains delta m plus and delta m minus for those two parts. And then we can apply changes to a table using the O plus operator, which will remove the orange rows as shown here and add the green rows. We define an O minus operator, which takes two tables and calculates a change set for us. And then what we can do is we can sort of combine the two and say that they should satisfy, well, if I have some table and I calculate the changes between that table and another table, and I apply those changes, then it should give me the same as the second table, in this case, m prime. So if we go back a little bit and we ask ourselves, well, okay, I know f of m, so we're going to say instead of x, we've now got m because we're working with tables. And instead of calculating f of x prime, we're now calculating f of m O plus delta m. Or we want to know what f of m O plus delta m is. And the answer to this is f of m O plus f of m O plus delta m minus f of m. And the problem is, well, okay, we need to recalculate the entire thing. And at this point, my old math teacher would always quote Faust and say, and here, poor fool, I stand once more, no wiser than before. And the solution is, well, we just hide it under some nice notation and get rid of the problem and sort that out later. So okay, let's try to incrementalize my expression. So let's say I've got this let n equals and let o equals, and I want to know o. And I start by saying, okay, well, I want to know delta n, so I'll replace that with the derivative, and then I get to G prime, and that requires n, but I don't know n anymore. So what can you do? Well, Colonel Elliott, again, yesterday did something similar. He just called it d hat, and we call it f dagger, which is basically just saying, okay, we take a tuple of f of m and f of m comma delta m, and then we can just automatically differentiate using a sort of chain rule type system. So if you look at this, you'll again say, you know, if you're looking at here in the opera house with your opera binoculars, you'll say, well, that's still not fast because you've just hidden things behind this fancy notation. And more specifically, we're calculating f of m for each step. So the question is, how can we make this faster? How can we optimize this so that it actually runs? And we'll start first by a small side condition which we need, which we like to call minimality. So let's say we have a change set, which in this case is the horizontal rows, and we consider the table state. Well, what happens if we try to add a row that already exists? We're working in set semantics, which means that's kind of pointless. And the same is for a row we're trying to delete that doesn't exist in the table. So we say something is minimal when we get rid of those entries that don't exist. And you can describe this in conditions by just saying, well, removed rows should be a subset of M. And the intersection between the added rows and the table should be the empty set. And then if we assume such preconditions, then we can find a lot of optimizations for these relational algebra expressions that don't rely on n or m. So in this case, we have the example of a set minus, where we say, well, if we know that n is a subset of n is a subset of m, and updated n is a subset of the updated m, and we know that everything is minimal to begin with, well then our derivative just becomes delta m o minus delta n. And this is great because it means that we can just take the change sets and perform calculation, and we don't need the database at all. And so using both a bunch of optimizations by Griffin and Libkin from 1995, so they also worked on a bunch of minimality preserving relational algebra derivatives. And in combination with those and a bunch of our own, especially for operators that were introduced in the relational lens paper, we were able to produce delta put functions, which only have a few places where they need to query something from the database. So in this case, we have one small query, but that's a lot smaller than querying the entire database, which would take forever. Right, and now to the results. So we've implemented this as a Links language extension. If you haven't heard of Links, go try it out. It's available at linkslang.org. We've just released a new version with the incremental relational lenses. Here's all the source code in one slide that we use. So it's basically a very simple concept of, you know, you create your lenses using the lens constructors, and you can then call lensGet to get the view. You can make a bunch of changes in whatever way possible, so it doesn't matter how that's done. And then you can call lensPut. We did a bunch of benchmarks. So this is a benchmark which was quite similar to the application I just showed you on the previous slide. As you can see, so the lines going up are basically the naive implementation, which recalculates the entire underlying tables, whereas our lines, which are sort of flatlining at the bottom, are the incremental version. And as one can see, there's quite a substantial performance improvement. There's more, so there's more benchmarks, etc., in the paper, and you can happily go and read it. Here's a more direct comparison between local and remote execution. As one can see, sort of latency does make a difference, especially because we do still need to query a few things. But overall, the performance becomes much more feasible than recalculating the entire database. So a bunch of related work. As I said, there's sort of three very important pieces that we extend on. The first is obviously the relational lenses paper, without which none of this would be possible. Then a great paper on incrementalization is the paper by Kai et al. Called The Theory of Changes for Higher Order Languages. I do recommend reading that. And finally, as I said, we used a bunch of optimizations like Griffin et al. And there's some relations to the delta lenses and edit lenses paper. So they tend to consider how updates translate in the notion of lenses, whereas we sort of try to incrementalize a state-based approach. And it would be nice to sort of see how those two fit together more closely, but we haven't done that. Some more future work is improving the language integration and possibly also experimenting with other optimizations. So we assume minimality, which you don't necessarily have to do. And it might be interesting to see how it is without. And, you know, there's more lenses that can be done. We also introduced a rename lens, which was fairly straightforward, which allows you to just change the name of columns. Yeah, and to conclude, so we had this existing work on relational lenses, which offered a great way to do this view update problem. It just wasn't practically shown how this would work well on realistic and large databases. And we used a bunch of incrementalization approaches to make it work on changes instead of the entire table. And we're able to show that this greatly improved performance when executing in sort of somewhat realistic scenarios. And we've implemented this as a linked language extension. So as I said, please go ahead, try it out, and let me know what you think. Thank you.
Okay, thank you, Rudy. So there's been a few questions asked by the audience. The first one is that you mentioned that you kind of assume a set semantics, whereas most databases actually have a bag semantics. Is that a problem for you, or do you know how to extend your work to handle bags?
Right. So in the most cases, we assume that we have a sort of system of functional dependencies. So that makes multi-set semantics sort of a little bit problematic. And I'm not entirely sure how well it would fit in with multi-set semantics. So there's some other work on incrementalizing relational algebra expressions in multi-set semantics, which was incremental view maintenance in a ring-less database, I think the paper's called. But in this case, as I said, because of the functional dependencies, I'm not sure that makes sense.
Okay. So you said that you treat the rows of the table as a set, but how do you avoid having to traverse the entire set if you need to check whether a row existed when it every now and then?
Right. So we maintain minimality as a condition and show that all of our operations are minimality preserving. So we don't actually go ahead and you know, make sure everything is minimal at every step, but instead we start out saying that our O- operator, which calculates a set of changes, calculates a minimal change set, and then we ensure that each step we take to convert it to an underlying delta doesn't affect minimality.
Okay. So this is kind of inspired by the original relational lenses work, but that was very typed. And did you use the same type system, or did you have to modify it in any way?
Yeah, so we use the same type system because we're directly incrementalizing those typing rules. Mm-hmm. So there's no need for changes there.
Okay, that's good. So there's another question about acid properties, and do your lens operations maintain these acid properties even in the face of potential failures or errors?
Which properties?
Acid properties.
Oh, right. So that is something we haven't necessarily looked at. We haven't tried to consider what happens, you know, when two different clients are trying to go to the database at the same time. In this case, it's possible that in the current implementation there are issues. There may be nice ways to work around this. I'm not too sure.
Okay, thank you very much.